Hi friends, let us discuss about central limit theorem. It is a very important topic in statistics and here is a brief note on it. We will come to this later, but before that we should do things practically and draw conclusion based on our observations. Then we will try to connect the dots between the theory and our conclusion. So let us import these modules and then we will generate 100 integers between 1 and 6. Okay, this is how it is. So let us write a note on this. We'll say the integers from 1 to 6 are getting generated randomly. And it is very important. The word randomly is important here. And the probability of each integer getting selected is 1 by 6 or 0.1667 or we can write 16.667. Okay. Now let us assign this sort of integers to a variable. And what we can do is we can write n is equal to any desired number, maybe 10,000, and we will write n here. So what is going to happen is when we execute this cell, 10,000 integers will get created and it will be between 1 and 6. And just see that variable. Okay, good. Now we have to check whether each and every number is getting generated in accordance with this probability or not. To do that, we should take a frequency count. How we'll go about it? Let us create a dictionary. For I in RV, di is equal to d get I 0 plus 1. And just see what it has done. It has created a frequency count for all those numbers. And see, these keys are being shown here randomly. They are not in order. If we want to see these keys in order, what we can do? We can create a dictionary comprehension like this. We will say I colon di for I in sorted d keys. Okay. Now the frequency count is being shown in an ordered manner. So all the keys are in ascending order 1, 2, 3, 4, 5, 6. And here it was not in order. Good. But how we have created this dictionary comprehension to sort this out? Look, this sorting has been done like this. If I rewrite D keys, this is what is given. And when we say sorted, then these numbers will get sorted in this fashion. Okay, this is there. And then after that, what we will do? We will say I for I in. And when we are saying this, we are getting the same value. Here, we can create a dictionary like writing like this I and DI. So what is the DI? See, I is coming. DI is what? DI is nothing but D1. D1 is what? D1 is this. And when we write D1, what we get? Its value 1682. So here it will be 1682 and here it will be 1. So dictionary is getting created 1 colon 1682. Then 2 comes. Then what will happen? If you see 2, this time 1606. So 1606 and I is what? 2. 2 colon 1606. So on, so forth till 6. So the dictionary will get created. Just see that. But before that, we have to change this bracket to curly braces. Okay, now run it. Look, it is already, we created this, right? Here. So this was only for explaining. Done. Now we can say D underscore sorted. Okay, good. Now what is our D sorted? Wow, D sorted is this. It is very much clear from this frequency count that all the numbers are getting generated more or less in accordance with their probability, that is 1 by 6. Correct? We can draw a bar chart. When we draw the bar chart, we will see the height of each and every number will be same. So in x-axis, it will be 1, 2, 3, 4, 5, 6 keys. And these numbers will be y-axis and the height will be same. And then we will call that this distribution is nothing but uniform distribution. All the numbers are having same frequency. That is what it means. So let us write that D sorted keys, then D sorted values. Okay. What happened? D sorted? No. Values. Dot values. Okay. Not underscore. See here. Let us write PLT show. What we are trying to prove here? We are trying to prove that when we generated randomly 10,000 numbers between 1 and 6, all the numbers are getting generated randomly equally. So all the numbers are equally getting generated. And if we are not happy with this bar graph because the sizes are not same, what we can do is we can increase the value of this n. And when we do that, this is going to be almost same. Before we do that, let us consolidate these lines. Let us take these two lines here. Let us remove this. Let us take this here. Okay, and take all these lines here. And let me remove these cells. Okay, fine. And we will say, okay, sure, good. So we will increase the number here and just see what happens. The height of each and every integer is same, right? The y-axis is showing this and the values are almost same. If you want them to be more perfect, increase the number. See, still the difference will be there, but compared to the number of numbers involved, the difference is going to be negligible. That is the idea. It is never going to be the same for all the numbers. The frequency count is never going to be the same for all the numbers. That we have to make a note of. And if we want to see, we can see. We say D sorted. Look, are they same? They are not. But since the number involved is so huge that the difference is becoming negligible, and hence this graph looks of same size, though they are not having same size. If we increase the scale, the difference will start appearing. Very good. So this is what we have done so far. Not now what we will do, we will, our next step will be, we will take samples from this number. RV is random variable and let us call this as population. What is population? Population means all the elements from a group, not leaving even a single element. Now, we will use this population and try to extract sample from it. And the sample size will be 30. How to go about it? We will say NP random choice from where? RV. How many numbers we will take? What will be the sample size? 30. Good. See what is happening. We have taken one sample from the population, right? So there are these many numbers. Okay. You can also reduce it. Okay. Let us reduce it. Let us make it 100,000 only. Okay. Fine. And from 100,000 we have taken 30 numbers. Then we will try to take mean of this 4.2. Let us run it again. 3.56. Let us run it again. 3.3. Let us again run it. 3.6. See what is happening. Randomly it is selecting numbers. Our sample, every sample is going to be different. And hence, when we are taking average of our sample, it is showing different numbers each time we are running this. 3.7, 3.4, again run it, 3.1. Okay, good. It is expected to be 3.5, but it will not be 3.5. But majority of the samples will give us mean as 3.5. Some will be very less than 3.5, some will be more than 3.5, much more than 3.5. Some will be slightly more than 3.5. Some will be slightly less than 3.5. But majority of them will be very close to 3.5. So what we will do now? We have taken only one sample. Let us increase the number of samples. How we can do that? For I in range, we'll say 100. We are taking 100 samples, and for every sample we are calculating mean. Then what will happen? There will be 100 means over here. And as we can see, we are expecting to get mean of each and every sample to be 3.5, but it is not the case. Look, 2.9, 4.1, they 4.1 is far more than 3.5, whereas 2.9 is less than 3.5, right? And we have several means, but majority of them are very close to 3.5. Okay. Then what we will do, we will take mean of these means. So let us do that. NP mean. So what is this? Mean of means. It is expected to be very close to 3.5, and that is the case. Okay, this is one conclusion. Our population mean, this is our population. This is 3.5. Our SAM sample means mean will also be 3.5. They are close, they are matching. Okay, this we have to make a note of. This is first conclusion. What is our first conclusion? Our first conclusion is the mean of our population will be equal to the mean of sample means. What is our second task to be done? Now we will see how the distribution of this samples means is going to be, how the distribution will look like. So we will take this entire stuff, and we will give it a name. Sample means we will call it. Okay. Now we will say draw a histogram of sample means. So we'll write sample means and we'll say the bin size is 10. See, this is how it is. Let us write PLT show. It is expected to take the shape of a bell curve. Normal distribution will look like a bell curve. Okay. If we are not happy with this distribution, we can increase the number of samples. It will get very closer to that shape. We will do that, but before that, let us try to draw a line, okay, across these bars. To do that, what we will do? We will say y is equal to, see, when we say PLT hist, see what happens. There are two variables. Okay, this is one list, the another is this. Okay, we can call this as y0 and we can call this as y1. And what is this y1? Y1 is basically the numbers that are there in x-axis. And in y0, these are the things. So look, 3 here, then 1 here, then 11, this height, 18, this height, 15, this height. So what we will do is we will put this in a variable called y. Okay, and y variable. So when we are putting this will be called y0 and this will be called y1. And if you want to see, let us see this. What is y0? Look, as I told, this number, this, the numbers in y-axis. And what is y1? They are these numbers. What is being shown in x-axis. Good. Now what we will do is, having put this in y variable, we can now say np lin space y1 dot minimum. From y1 variable, take minimum, that is 2.8. From y1, take max. What is that? 4 or more than that. Okay. Those numbers are not visible here. And then we make 10. So when we write this, what happens? Just see. This is what happens, right? From 28 to 4.06, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers have been generated. We can also write 20. Then 20 numbers will get generated, right? Like this. But lower number and highest number will be same. And in between, it will create several numbers having similar distance between two of them. Correct? Okay. Now what we will do, let us write the next one. So here what is that? We will put in a variable called z. And then we will say plot Z and then Y0. Look, what is Z? Z is going to be our this stuff. This stuff, right? Okay. And then what is Y0? We already discussed what is Y0. Y0 is nothing but these numbers, whatever is there in Y axis. Correct? Let us run that and just see what it will do. PLT show. Did. As was discussed earlier, if we are not happy with this shape, we can increase the number of samples and then it will start looking like a bell curve. We will do that. Let us consolidate these lines. Here we will put, okay, very nice. And then let me remove this. And what we will do now, we will increase the number of samples. Maybe we will make 10,000. Just see how it looks. This is how it looks, right? If we try to see it separately, we can do that as well. We will say PLT show. See, this is our histogram. This is our curve. It is a bell curve. It is taking the shape of bell curve. Okay, and this is typically called normally distributed data set. Okay, so let us superimpose line graph like this on top of this histogram. Now, what we conclude here, this is all about distribution. See, as was discussed earlier, most of the samples mean happens to be 3.5 or very close to 3.5. Hence, the bar here is having this sort of height, right? The height of the bar is more than other bars. The bar which is near 3.5. Okay. There are bars far away from 3.5. If the number is, if the mean is much more than 3.5, like 4.5, the bar size is very less. Likewise, if you take very less mean, that is 2.5, the bar size is very less. But there are some numbers which are more than 3.5, not much more, more, like 4. And here it is 3. So this is making a step like this, right? And this is what is called bell curve. This is what is called normal distribution. Okay. So earlier we drew the conclusion that our mean of population and mean of sample means will be similar. And the second conclusion is our population is coming from uniform distribution, and we have when we have taken several samples and taken the mean of each and every sample, and when we are drawing histogram for those means, it is taking the shape of normal distribution. That is the conclusion. Okay, so what we can do is, let us go and copy this as well here. Okay, fantastic. And let us remove these things. At least this one we will remove. Let this be here, here. Okay, because it is all about average of population, average of sample means. And when we run this, again, we will have this as well as this. Now is the time to read the note, which we did not do earlier. What it says, central limit theorem, a statistical theory, states that as sample sizes get larger, the mean of all samples will be approximately equal to the mean of the population. Have we seen that? Yes, we have seen. Here, just see 3.48, 3.5. What it says? Increase the size, increase the number of samples, then it will get closer to 3.5. Look, now I made it was earlier 100, now it is 1000. Correct? That is point number one. Even if we have number of samples only 100, if each sample contains 300 numbers instead of 30, this will also contribute to the same thing. It will bring things closer to what? 3.5. See 3.49. Let me increase this again slightly, maybe make it 500. See 3.5. So sample size will have impact. Even the number of samples is going to have the impact on mean. So what they are saying, let us keep this 30 only. As the number of samples increases, we are getting 3.5. And even if I don't increase this, if increase this, only this, assuming that it remains maybe 100 and I make it very large, maybe 50, this will tend to get closer to 3.5. And what is 3.5? That is the mean of our population. Just see. So this is done. We have changed the sample size. We also change the number of samples. In both the cases, we are seeing that the mean or sample means is getting very close to 3.5. Okay, good. Next, the distribution of means will approach normality. What does this mean? Look, it also says regardless of whether the population has a uniform, normal, binomial, or any other distribution. But our population distribution is what? It is uniform distribution. It is basically saying no matter what sort of distribution your population belongs to, when you take the distribution of means, right, sample means, it will give you a bell curve. It will be normally distributed. That is what it means. And that is the case. This is RV is uniform distribution. From here, we have taken many samples. For each and every sample, we calculated means. And for all those means, when we drew this histogram, it took the shape of bell curve. Basically, this is normally distributed data set now. And that is what it is saying. So, this entire stuff is understood now. So, we have concluded that yes, so far as the mean of all samples will be approximately equal to the mean of the population is concerned, we have checked that. And distribution of means will approach normality. That also we have seen. So, that is all about central limit theorem. Okay, we have checked only for uniform distribution data coming population belonging to uniform distribution. We can check for other distribution also in the upcoming video. Thanks for watching, and I will see you in the next video.